Well, hello, hello, hello. Welcome and good morning, everyone.
Good morning.
How are we all doing today?
Doing good.
Fantastic. Welcome back to Monday in our second week. So, as you can see, I am not the usual guest Monday speaker. I'm here filling in a place, but hopefully I still have something that's going to be of interest to you. Artificial intelligence and machine learning, certainly popular in the media at the moment, popular in our society, in our colloquial speak. But what is it at the end of the day? Now, we're here to do marine engineering and naval architecture at Webb. We're not so much going to be computer scientists, still you could be, but that'll be done outside of here per se. So this is going to be a little bit of an introduction overall, very high-level introduction to AI first, and then dip our toe into some more technical aspects of what it means to be artificially intelligent or what machine learning is that underpins it. So, of course, that's all well and good, but why me? I teach engineering classes here, so why am I talking about AI? Well, the short answer is I'm not an expert, but for various reasons over the last several years, I've gotten to know more and more about it, and my hope is that I can bring it to you all now. So I first kind of exposed to it through my own doctorate program, through classes, and I used it a little bit in my dissertation. Used the reinforcement learning model in my dissertation. It wasn't a major portion of it, but I did use it, and that's the title of it there. Separate to this topic, though, collaboration and systems of systems, not to do with this. So if you want to learn more about that, we can talk about that separately. But I'd also like to thank, because after I had finished my PhD, I've been teaching some classes through George Washington University, where I got my PhD, in artificial intelligence and machine learning. So I'd like to thank the couple of professors over there, Hamza Al-Sarhan and Amir Adamati, for providing some of the materials that I'm using for this as well. And to make this a little bit more engaging, I've also drawn some content from Professor David Malin at Harvard, who, if you're not a computer scientist, but you're interested in some of those topics, I highly recommend his classes or his courses. They're very accessible. And Stephen Welch from Welch Labs online, he makes nice visualizations of machine learning models, so I've used some of that as well. So hopefully this will be a little bit engaging for you. And I'm going to start out with a little bit of interactivity. So first I'm going to play a video, and then I'm going to ask you some questions afterwards. So work with me over the next few slides, and hopefully we can do well. A little bit creepy, huh? All right, now, everyone who recognizes who that is? Who is it? Well, it's supposed to be Tom Cruise, right? Well, I sort of say supposed to be. Of course, it'd be a little weird for Tom Cruise to look into his phone and then try to do a fake magic trick with his coin, because it's not real. Despite how convincing it may be, that entire video is done completely with this so-called AI, generative artificial intelligence. Generative artificial intelligence, meaning that it was generated out of effectively nothing with a certain model. Okay, well, let's try something a little bit better, a little bit more interactive. Here we got two images. So, one of them is real, one of them is fake. Which one is it? Raise your hand if you think it's the one on the left. If you think the real one is on the left. Yes, real one on the left. Okay, we got hands. I think there were a couple before. Okay, real one on the right. Okay, that's pretty much everyone. Anyone unsure? Okay, a couple, that's fair. Okay, good. So most of you got it right. Now, what's the reason why? Someone who got it right. Joe, why do you think that the one on the right was right and the one on the left was fake?
On the left, like her forehead and her eyes disappear disproportionately, and I feel like testing it out, and just like overall kind of too perfect in a way that
Okay, there's a usual response right there. It ends up sometimes looking too perfect or perhaps too polished. Okay, let's try it again. Is the real one on the left? Raise your hand. Okay, few. So a little bit more differentiation than last time. Okay, real one on the right. Okay, a lot more. All right, how confident are we? Anyone unsure? Okay, no, we've got a lot more people unsure. Well, that's good. If you were unsure, because it's a trick question, they're both AI generated. But they can be a little bit difficult, right? Certainly without some context, it can be difficult to tell them apart. Okay, one more. This is an article from about 6 months ago, I think, in the New York Times. Did a fourth grader write this or ChatGPT, effectively? So we've got two essays. The first one, I like to bring a yummy sandwich and a cold juice box for lunch, and sometimes I'll even pack a tasty piece of fruit or a bag of crunchy chips, and as we eat, we chat and laugh and catch up on each other's day. Or, my mother packs me a sandwich, a drink, a fruit, and a treat. When I get in the lunchroom and I find an empty table and sit there and eat my lunch, my friends come and sit down with me. First one, real? Essay one, real? Second one is real. Maybe. Okay, any unsure? Okay, still a few people unsure, which is fair, okay? Good to be skeptical. Well, you are indeed right. The first one was not real, generated by this AI. Okay, so it's still not perfect, and that's going to be one of the themes and takeaways from today, is that it's not perfect, but under the right set of circumstances and without perhaps some context, it can be difficult and certainly make us question what is real and what's not. So, fast forward to today, there has been a proliferation of various kinds of large language models, as well as other multimodal models, so-called, that underpin generative intelligence, generative AI, I should say, that can produce all sorts of new materials, new content, answer questions, and seem to do really impressive tasks. Now, they're not perfect, like I said, and we'll see some reasons why, but we're going to look at first, instead of this generative artificial intelligence, we need to understand a little bit of what's going on underneath the hood. So we need to start with just artificial intelligence, and perhaps some of the motivations as to what makes something artificially intelligent versus not. Now, you've probably been exposed to artificial intelligence in some way, in a very broad umbrella term. Email spam filters were an early use case for various types of so-called AI models to separate out your junk mail and your spam from your real emails. Quite frankly, nowadays, now I know a lot of you probably didn't have email 10, 20 years ago, but many years ago, email was much more rife with your spams and your newsletters and your promotions and whatnot. Nowadays, you hardly get any of it, quite frankly. Doesn't mean that it's not always out there, it just means that the filters have gotten much better, largely because of artificial intelligence techniques. Handwriting recognition, okay, also not a new concept. The post office has to read all of your handwritten addresses. Sometimes they do it by humans, most of the time they do it by computer. A computer reads what you've written on your envelope, and it deduces what you've written as best it can. And it does it pretty well. Content recommenders. I'm sure someone's used YouTube or Netflix, right? And perhaps you've gone too far today where sometimes it's hard to find something that's not related to what you've just been watching for the last several months, because it just keeps recommending to you stuff over and over and over again aligned with what it thinks you like. And for the most part, that's fairly true. There's a wide swath of things out there, of course, that you probably haven't seen. And finally, games. Games, often you'll have games, you play a game, and the computer player is called the AI, quote unquote, right? Now, is it actually an AI? Traditionally, probably not. And we'll see an example why. Though today, we could move more towards that. I'm going to use that because it's fairly interactive as a basis for justifying what our artificial intelligence is initially. So, does anyone know what this game is called? Breakout. There we go. It's not a new one. It's actually a thing put out in the 70s or 80s originally. Very simple. You have a bunch of bricks or blocks up top. You have a ball that bounces back and forth between the top and the bottom, and you have a movable paddle on the bottom. That's you, the player, slide back and forth. Now, just by nice, easy intuition, all of us in here should say, okay, if the ball is right there, where should I move the paddle? Maybe a little bit to the left. Now you might say, okay, it depends on where the ball's moving, right? Okay, but even if you didn't know where the ball was moving, you do know that in breakout you need to hit the ball with the paddle. And so no matter what, by the time that ball comes back down to the bottom of the screen, you want to have the paddle be right underneath it. So at the very minimum, you could at least move it to the left just to be sure, and then just essentially follow it around the screen, just to make sure that it's always underneath there. Okay? Well, that's nice and easy. That's a logical intuition for us humans who might play it. Could look at that pretty obviously. But how could you do that for a computer? We could turn that into a simple set of decisions, right? This is fairly easy. There's only one set of decisions to make, one agent, one action that you need to make. It's the paddle. So, quick question then, like that. Is the ball to the left of the paddle? like it was on that last screen? If it is, what do? Move the paddle over there. Easy enough. Okay, what if it's not to the left of the paddle? Okay, well, so it may not be obvious, but there's really three options, even if it's not only there. But we can then check if the ball is then on the right side of the paddle. Otherwise, you could always slide it over to one side of the screen, and then your loop would kind of get stuck. So is the ball to the right of the paddle? We have to ask ourselves again, if it is, then what should we do? Move it to the right, easy enough. If it's not, then what? If it's not to the left and not to the right, what should we do? We should do nothing. Don't move it at all so that it's right there. This right here is our first exposure to what we'll call a decision tree. A decision tree is a concept that's actually very, very old. I don't really know the origins of decision trees as a kind of heuristic for laying out choices or structures of things, but it's heavily used more recently, not only in artificial intelligence and machine learning, but in a wide variety of process analysis, business analysis, economics, and things like that. All it is laying out decisions, strategic decision making. Okay, strategic decision making. Now, this is fairly simple decisions, but perhaps we can make this a little bit more sophisticated. So let's try a little bit more sophisticated of a game. We'll talk about tic-tac-toe. If we've all played tic-tac-toe before, at least seen what it is. So if I'll ask you then, given this board, if you are O, if you're player O, where should you go next? Middle left, right? That's pretty obvious. You put it in the middle left, boom, you get the 3 in a row, you win. Fantastic. Okay, let's try that again. If you're X, what should you do? Also middle left, because then you want to prevent O from winning. Okay. So let's turn that into a set of decisions then, a la a decision tree. So the easiest, the simplest way to look at this is that for any turn, no matter who you are, player O or player X, can you get 3 in a row this turn? Is there somewhere on the board where if you place one move, you're going to get 3 in a row because then you'll win? If yes, what do? Well, you simply play that 3 in a row. That's easy enough. If not, then what do you check? If someone else can do it. Check what your opponent does. If your opponent can get 3 in a row, now you don't want them to win, even if you can't do it. You still don't want them to win, though. And so if your opponent can get 3 in a row, what do? Well, you block them. You stop them right there. You put it wherever that 3 in a row is going to be to prevent them from winning. And then what happens if that's not possible or if that's not available? Well, that's not so obvious then, right? Where do you go? Well, it depends. Depends a little bit on what the rest of the board is. Okay, so let's construct a little bit more of a numerical way then to assess a tic-tac-toe board to maybe fill in that blank. Fill in the blank to that question. Okay, computers can be very good at playing games like this when we can construct games or scenarios like this in terms of a mathematical function, a number, numerics, things like that we can then process. So let's do that here. So our goal is that given a set of inputs and outputs, we want to optimize something effectively. Optimize our chance of winning. So if we do that, okay, in order to optimize our chance of winning, we not only want to win, but that might also try to minimize our opponent's chance of winning. So that dichotomy, both maximizing your own chances as well as minimizing your opponent's, can be put together. Now, it's a little bit more specific than that at a mathematical level, but we can put that together into a function called a minimax function. Minimax, combining both minimum and maximum together. Now, to go through this principle, we need to assign some numbers, because numbers work better for doing math on them. So this board on the left, I'm going to say this is a final state board, right? O has 1. This board, I'm going to assign a numerical value of -1. This board is a tie. If it's a tie, I'm going to assign it a value of 0. And if X wins, I'm going to assign it a value of +1. Easy enough. Okay, basically, if one of the two wins, if O wins, it gets a -1. If X wins, it gets a +1. If it's a tie, excuse me, it's a 0. So if that's what the score of a board is, what should player O's goal be in terms of the scoring? You want to minimize, right? O by itself wants to minimize their overall score. Now, if O cannot minimize their score, i.e. because X is about to win, what then do they want to do? At least force a tie if you can, or in other words, maximize their worst outcome. maximize the minimum in that case, that's the minimax. Okay, x does the same thing, just with swapped numbers. Now you could swap these numbers, you could choose any numbers so long as they're differentiated between each other, it's okay, but this is what we use because it's fairly easy. Okay, so, for those paying attention, what value should we assign this board? 1, right? Easy enough, x wins, that should be a +1. Okay, so let's walk through this with a game. This is the scenario we just had, okay? Or a similar scenario, actually, slightly different board, but similar scenario to what we had. Given this board right here, it's O's turn, okay? So you're player O, you're faced with this board. You have 2 options now, right? There isn't an obvious choice as to what you should do to either maybe win or not. You have 2 options. So which one should you do? Well, we'll go through them explicitly rather than just saying, okay, there's an obvious one, right? Our players out there, human players, probably see there's an obvious choice here, right? But the computer doesn't know what an obvious choice is, so let's write it out a little bit more explicitly. 1, they can go in the top left block there. O could go there. If O goes there, where does X have to go next on X's turn? Right in the bottom middle, right? But if X does that, then X wins. So going through that whole scenario, that final board has a value of +1. Now, we can also just basically translate that back up to an equivalent value on the board before it, because there is no other choice there, right? This board will have to go into that final state from that second one to the third one, and so basically we can say that's also an equivalent score. Okay, but that's not the only choice that O can make, so O can go into the other spot that's open, the bottom middle, and then in that case, X has to go in the top left, and when we look at that, then that's a tie game, and the value of a tie game is 0. And then through the same principle, because you can only make one move, we can bring that 0 back up. So now O, since O's choice right now is faced with this board, and now we've run through the options, according to our principle of trying to maximize our personal score, but in this case for O, because O is assigned the negative values, we actually want to maximize the negativeness of it. So which choice should O make? One over here on the right, right? Easy enough. Because if O makes this choice, that has a value of 1. Now O wants the maximum negative value it can get. 0 is more negative than 1 in that respect. Okay, easy decision making. Now again, this is fairly obvious for a human, but now we've told the computer exactly what they can do, and all the computer has to do is do a fairly trivial calculation and then make a decision on it that's guaranteed to do better, at least, than losing. Okay, so we'll assign that then as the minimum value of 0. That's what O should do. Now, what happens when we go one more step? So obviously, we don't start tic-tac-toe with a board that looks like that. We start tic-tac-toe much earlier on. So what happens when we take one more piece out of that board? Well, now the decision tree gets much bigger. It effectively doubles. Okay, it's not perfect, but it effectively doubles, such that every time you take one more of those choices out or you move one more turn back towards the beginning of the game, your decision tree keeps doubling and doubling. It's actually an exponential relationship. So already here now with 3 choices to make, you have several more branches to have to go down. There's 3 possible outcomes where there's a win. We have several different values. If you go through all of these values, okay, because we've gone a turn prior, it's now X's turn rather than O's. And so X, looking at this board, can go down the same process of the decision tree, assign values to all of the end states, work those values back up by choosing whichever one is best for them. And that should actually say maximum value because it's X, but you get the idea. X wants to maximize their value, so whatever the maximum of this is, it ends up being a +1 out of those 3 options. If we go down the left board, it's 0. This middle board is a -1. This option over here on the right is a +1. That's what X should choose. Okay, great. Easy enough, right? That makes sense. And now, hopefully, if you, in theory, you follow this principle, you playing tic-tac-toe, in theory, now can never lose. There is essentially a procedure to guarantee that you will never lose in tic-tac-toe. You may not always win, but you will never lose. You can always force a tie. But to do that requires you to do what if you're going to start out the game and then make sure that you can guarantee a tie every time? It means you have to go down these decision trees. And as we see, as we keep going back farther and farther back up the board or back up the game, it's going to get really, really complicated to keep all of those different pathways in mind and calculating the minimum or the maximum score, etc. In fact, of all possible pathways for 2 players to go back and forth in a particular configuration to play tic-tac-toe, including symmetric boards, but there's a whole kind of theory around the combinatorics around board states, but regardless, including all the symmetric possible arrangements of the board, and two players going back and forth, there are over 255,000 unique ways to play tic-tac-toe. So I'll guarantee you that you've never played every version. Now, tic-tac-toe, though, while 255,000 kind of hard for a human, I'll grant you, fine. I can't keep 255,000 different end states in my mind and then pick one. Not actually that hard for a computer. A computer can chug through 255,000 calculations or even multiple calculations of that pretty easily. But let's try something even a little bit harder, right? Tic-tac-toe is not the hardest problem in the world. Let's try something like chess, okay? Chess, first four moves only. First four possible moves, so that's both players. So one player, then the second player, that's one. Second player, second turn, two, third turn, etc. First four turns, 85 billion unique combinations. Across all of the possible combinations, they get whole pathways, right? So this is from the beginning, blank board, all the way down to a final game. It's actually not really a known number for chess. It is known to be a finite number, but we don't actually know the exact number because of all the different combinations thereof. But it's estimated realistically to be about 10 to the 40th possible unique pathways from beginning to end. Now that's excluding any illegal moves or odd combinations and ending at realistic end states. There are, of just arrangements of pieces on the board given their rules, something like 10 to the 120th estimated unique combinations if you just allow pretty much any combination. Illegal moves, kind of repeating game moves, things like that. It's called Shannon's number if you want to read more about it. That's not really realistic, but regardless, that's a really large number. And no one's actually computed it because it's so large and kind of difficult. Okay, you might have heard a few years ago that there was a computer that played the game of Go. Anyone know what the game of Go is? Ancient game, right? So it's a grid. You've got white and you've got black tiles or little tokens, and you place those down on a grid, and the goal is to try to capture your opponent's pieces and own up to particular configurations on the board. Now, it's a much larger grid of possible options than chess is, and different arrangements that the pieces can move. It ends up having a lot more combinations. In fact, the first four turns only, 26 quintillion different options. A huge number, uncountable number, quite frankly. And yet, between chess and Go, over the last several decades, tic-tac-toe not so hard, right? We just walked through it ourselves. Chess, IBM's Deep Blue, effectively beat that as a computer. Now, how it did it is a little bit different from what the player for Go did, AlphaGo, a few years ago, beating the world champions at Go, a computer. Now, for chess, there's a lot of possible options there. And especially for Go as well, it's basically a deterministic set of outcomes, an equation, a function that can be calculated and optimized and be guaranteed to be optimal. Instead, we use something called machine learning. Again, you've probably heard machine learning again, but what does it mean to make a machine learn? So here we go. Volunteer. Who wants to come down? Tyler, I love it. He volunteered. Come on. All right, you've got the frying pan of science here, and in it is our demonstrator hypothetical pancake of science. Now we're going to go through a little bit of a demonstration on this on how machines learn, or one way on how machines learn. You stand here in the middle so everyone can see. You don't want to hide behind the podium, sir. We got to see your successes here. Tyler's going to attempt to flip the pancake. Easy enough, right? And as he does so, I'm going to provide him some feedback. So, go ahead. Good. All right. Try it again. Okay, a little bit hesitant, but first, you still succeeded. Keep going. Nice. Almost slipped it out of the pan. He's getting the hang of it now. Good. Good. Oh, bad. Bad, Tyler. Okay, very good. Thanks very much.
Yeah.
Okay, easy enough, right? Now, Tyler's probably seen how a pancake gets flipped or something in a pan before, so he's got some information to go on with that. He's got a lot of information in his hands and the situation at hand. And so my feedback, okay, it's useful. When he does it well, we say, good job. If not, then we say, bad job. And then he feels bad about it and he wants to fix his actions. But that basic principle there, irrespective of everything else that Tyler has going for him, is a principle of how we can teach a machine to learn as well. And we, in fact, have done that. This isn't new, per se, but this has been demonstrated as well with a robot flipping a pancake. Simple setup, robotic arm. Now that robotic arm obviously has a couple of actuators in it to move it, as well as sensors to measure the angles of those motors. We've got a pancake in there with a pan with a couple different pancakes. Now the pancakes have little dots on them so that the researchers can keep track of what the actual motion of the pancake is. Now this is interesting. We'll talk more about this particular process. But a researcher here puts the pancake in the pan and then moves the robot's arm for it. So the robot's going to measure effectively, while that's going on, what is a good action, and then it attempts to do it itself. Now, of course, it's not great the first time around, right? You're just slapping a pan and a pancake in the hand of a robot with no eyes. It has no idea what it's doing. It's just blindly guessing, but it will get there eventually so long as they provide appropriate feedback. And so what they do, after they'll show here in just a second, is the little dots on the pancake, their fake pancake, can then be measured or tracked with cameras, and then the motion of those dots can be fed back to the robot. And what they can say is when that motion of those dots goes in the right action, there it is, so here's us tracking the pancake. When the motion of those dots goes correctly, we say, good robot, do more of that. When it doesn't, we say, bad robot, stop doing that. Easy enough, right? That's all it is. And even then, so long as it has that information, after about 50 trials or so, the robot pretty successfully flips the pancake every time. Now, there's two things at play here. So this is an example of what's called reinforcement learning. So much like we just had with Tyler, when you provide that immediate feedback to something that the robot or the computer, machine, etc., doesn't already know something about, that's reinforcement learning. That's one way to teach a computer or machine how to do something. You set up a very simple environment. You tell it to do a thing, and then all you do is say, here you go, reward for doing it well, penalty for doing it bad, and you just keep repeating that. That method is really conducive to playing games, so much like the games we'd seen before, or like that breakout that we had talked about prior. Very effective for training machines in how to play that. But there's an additional piece to this. Reinforcement learning is a whole branch within the machine learning world that works for some applications and has a certain setup. But in this example, while the researchers provided that feedback on what the pancake was doing, and so fed that back to the robot to know what was good and what was bad, he also at the beginning did what? The researchers showed the robot effectively what to do. And that actually lends to another concept in machine learning. When you provide what you want out of the model or the algorithm or whatever, what you want the end state to be, and then give it the starting information and say, computer, go figure it out by some means, by some algorithm. That principle is called supervised learning, that category of machine learning called supervised learning. Now, supervised learning actually more so the traditional place where machine learning lies than oftentimes the workhorse models. Workhorse models meaning simple models that can process data in everyday life. Okay, a lot of models today, or a lot of traditional uses of machine learning, use various kinds of supervised learning models, as opposed to what we'll talk about later with some of the neural networks today. But supervised learning is where it's at for the most part. So let's start with really simple. A linear regression. You've probably seen a linear regression before, right? I hope so. You've drawn a trend line in Excel at least, right? Okay, a linear regression takes in two pieces of information, say an x and a y coordinate, a couple of dots, and then tries to fit a line through it, right? Nice straight line such that some error is minimized. Traditionally, a root mean squared error or mean squared error. Okay? That's a simple linear regression per se. And the equation of that line is nice and easy. You know, traditional equation of a line, y equals ax plus b, mx plus b, whatever you like. Okay? Now, for machine learning purposes, let's translate this to a machine learning perspective, right, where we want to minimize the root mean squared error here. I'm going to give you a couple terms here for the machine learning parlance, because with traditional or simple linear regression, if you're going to do this in the lab, right, the x value is going to be some independent variable, and then the y is some dependent variable, where one has a causation on the other, or otherwise you're trying to see some relationship between the two. Okay, now with machine learning, it gets a little bit less clear about what an independent versus a dependent variable is or like that, so we give it some different names. So we're going to call the x's here a feature. That's the term that we're going to give to these equivalent x's. Features. And then the y is called an output or a label. If it comes from this blue line, so the value of y comes from that blue line, it's an output. If it's one of these green dots, it's a label. Okay, separating what is the data that you have versus what the model is. So a model has an output, data has a label, effectively. Okay, that's machine learning terminology here for it. Now, this is nice and easy when you have one feature then and one output. We can visualize that. What happens when you have two features, though, and one output? How would you put a regression through that? More of a surface, right? Becomes multidimensional. Instead of this nice two-dimensional plot, we'd have to make a three-dimensional plot and a surface, right? Then we have our two x's on the bottom, and then the y is a third. Okay, fine. How about 3? Uh-oh. Well, that's hard to visualize. It's hard to visualize the fourth dimension there. How about 5? How about 10 features? How about 100 features? How about 1,000,000 features? Okay? You can have that. Data doesn't care. Data's got as many features as it likes, which are characteristics of data that you might find interesting. You can collect loads of features. So we don't want to be constrained to just having 1 or 2. That's not all that useful. So a machine learning linear regression, all that does is extend that equation out. However many features you have, we'll just say, okay, given our outputs or our labels, we'll just keep slapping on another feature, another feature, another feature, another feature, another, etc. However many we have. Okay? We still have our output, our label. And if it comes from the model or our equation, it's an output. If it comes from our data, it's a label. All of our x's now are all of the features we can have. But now that we've added all these features, from our equation of the line, we had a coefficient on our x, right? We still have to carry those coefficients forward so that we can modify the actual shape of the line. We call those, in machine learning parlance, weights or parameters. Weights or parameters. But all it is those slope coefficients. Now, again, it's not so clear what a slope means in 100-dimensional space, but the principle, the mathematical principle still exists there. All right, so this is our equation then. So what I'm saying is that you can then, for however many x values you want, collect them together and say that they might all contribute to some y value that you're interested in. But you need now to get this to minimize error, right? That's how the linear regression gets calculated in Excel. You calculate the root mean squared error of all of your points, and then you minimize that by adjusting those parameters. The same thing happens here. It's not so easy to do it for every single one of those weights in a nice, clean algorithm like you can with a fewer number of them, effectively using linear algebra. It takes a lot of computations. So instead of analytically computing what the minimum is, we can take a little bit of a, not say shortcut, but a numerical process. A numerical optimization process rather than an analytical one. And this algorithm will go something like this. First, you're given your equation and all of your data. First, you just slap a number into those weights. Doesn't matter what it is, just put in a random number to start. That's called initializing them. Then, you take a data point, and you input that data point into all of your x's and your y. So when I say a data point has a set of features. You can think of them as different columns. And at the end of the columns is your y or your output, whatever you find interesting about your data, and you want to find a relationship between the y and all of the x's. So you take one of those data points and you just put it into that equation that we've just written there with the random weights. Then compute what the output is from the equation and compare it to what the label is. Compare it to what the y associated with all those features are versus what the model is saying. Now, presumably or likely, it's not going to be perfect. It's not going to be even close, probably. And so you're going to compute an error. There are multiple ways to compute an error, but root mean squared error is one of them, or mean squared error is one of them. Compute an error term between what you think it should be and what the data says it should be. And then depending on the size of that error, go back and change those weights. Update the weights, we call it. Updating the weights such that we reduce the error. Now, we don't know how much. Okay? We reduce it by a certain amount. There's a parameter for that. It's called learning rate, and affecting that kind of changes what your training process looks like, but you change it by a certain amount. Okay? Now, the details of going through this in an implementation is kind of technical. If you want to talk about that more, we can talk about it later. But this is the basic process, basic pseudo-algorithm, if you will, for how we can train the model. Because eventually, if you keep updating these weights to reduce the error, eventually your error will get minimized. Usually. Most cases it can be if you've constructed the problem well enough. But you repeat until your error has been minimized. And then, there you go, you've got your equation. You'll notice this works just as well for just one variable. It's the same process. We're just extending out to all of these variables, all of these different features. Now, when we do this with linear regression, that y becomes that output, usually a number, right? If you think about it in the lab, you predict some number that it could be. Fine. That's one task. We call it a task of what a supervised learning model can do. It can make a prediction, a numerical prediction. There's another major task, and that's called classification. So classification, instead of trying to predict a number, instead tries to say, all right, given some characteristics about the data, I want to separate them. Say things that are similar to each other go over here, things that are similar to other things go over there. Be able to draw a line between them, or some shape between them. That's called classification. So given these two data points then, as opposed to the collection I had before, these two data points, I want to separate them. Now one's a blue data point, one's a red data point, which means they have two different labels. Before the labels were all the y's. Now our labels are called classes. There's two classes, class blue and class red. These two data points have one of each according to wherever their position is. Now, how could I separate these two? What would be a nice, easy way to separate them? With an equation. A line, right? Just slap a line through it, much like we just had. Just put a line through it, and everything that's above that line or greater than the number calculated by that line is one class, and everything less than it is the other class. Okay, nice and easy. So we'd modify the equation of the line a little bit. We still have our x and y and the offset, or so-called bias term. The bias term here is that c, right? The intercept, basically. The intercept in the simple equation is called the bias in machine learning equations. But we modify that a little bit, and I move the bias over, and I just set it greater than or equal to some standard value, make it 0. Now I make it an unequal sign so that whenever that's true, it's one class. Whenever it's false, it's another class. So basically everything greater than the equation is blue. In this case, everything less than the equation is red. Easy enough. Okay, cool. But two data points isn't all that hard to separate. Again, we could do that really easily ourselves. Okay, so what happens when we add another data point? Are we still good? Easy enough. Yep, still separates the two. How about now? Okay, easy. How about now? Okay, well now our line has a problem. So we'd have to adjust it a bit. Can we still draw a line to separate them though? Yeah, we can. We can modify that line a little bit, and it would pass, above this red, something like this. So we just have to modify the line a little bit through a training process, but it's so-called linearly separable still. Okay, how about now? Oh, now we're in real trouble. There is no one straight line that I can draw that will cleanly separate all of the blues from all of the reds. Right? This one down here just throws a wrench into the works. There's no way to do it with a single straight line. And data is usually not clean like that then, so it's usually not so linearly separable, given a lot of data points. Okay? We can kind of see, yeah, generally that there's some blue more so on the top left and there's some red more so on the top right, but they intermingle a little bit, and there's some points on either side, and I can't draw a straight line through it. All right, so what can I do about this? Tyler? Okay, good ideas. You could take two lines. Now, two lines works in some cases. That's called the exclusive OR problem being solved there with two lines. But you still probably can't do this problem with just two lines. You need a bunch of lines, and then that gets a little bit repetitive. A more efficient way would be using a nonlinear approach. So instead of just a straight line with x's, you'll notice there were no powers on any of those x's. They're all just x. They're all linear versions of x. You could maybe use a polynomial, or a higher-order polynomial with a squared term or a cubic term in there, a nonlinear polynomial equation. You could do that. Now, for anyone who's tried to calculate or perhaps solve a high-order polynomial equation or nonlinear polynomial equation, how easy is it to solve that when you've got squares, cubes, quartics, quintics, x to the 10th power in it? Yeah, not so easy. It takes a lot of computation to get that down to a specific number, a specific solution. So that works in some cases, but it oftentimes becomes computationally expensive after a while. So there are other techniques instead of just using other versions of regressions, linear and nonlinear regressions. How about this data set? Okay, a similar situation. We can clearly see two clusters here, a large cluster of blue, a large cluster of red, but they've got a funky shape. They're kind of like two half circles that have been interleaved with each other. Okay, this is from a synthetic data set called the Moons data set that you can modify some parameters about, but it creates a nice training problem for nonlinear data separation. What do I have up here? Not just regression, but decision trees again. Decision trees, much like the decision trees we talked about before for playing games, we can use those to separate data just as much as we can use them to choose an optimal game output. So effectively all you do is, given a set of data, start with a line and draw that line through the data, and see, split the data into two pieces, right? If I was to draw a line straight through this, I'll pick a line, it'll go somewhere through there, I'll split the data into two. Now in each of those splits, there's going to be some blue and some red, because again, we can't linearly separate them. There's some blue and some red. So all the decision tree does is that's what happened in the first node. I'm then going to say, in each of those groups, repeat the process. Draw another line in the subgroup, in the subset, and split that one as best you can. Again, it's probably not going to be perfect, but it's going to get closer. Then in each of those subgroups, split it again, and then each of those split it again, and so on, until you get to a final split where all of one subgroup is blue and all of one subgroup is red. And you do that across the entire set, and you end up with a tree that looks like this. This is the actual decision tree, or a decision tree, that I computed for that data set right there. And it shows then, okay, so the colors represent how much of each color is in that subgroup. So each one of these boxes is a subgroup that's been split. Our whole data set is up here at the root node. We first split, we get mostly blue on one side, mostly red on the other, but it's not perfect. So we split again, we get a lot of red out of one and more blue out of the other, and again, we keep splitting. The leaves, or the final or terminal nodes, they're called at the bottom of the decision tree, should all have nice clean blue, red, blue, etc., so that they're all uniformly red or blue. Now, for a separation then, this isn't a nice clean singular equation where you just plug in a number and you get red or blue nice and out. But now you can take a data point, start at the beginning of that decision tree and see, does that data point fall on one side or the other side of the first split? Then after that split, does that data point fall on one side or the other side of the second? And then the third, and then the fourth, and eventually you'll make all of those decisions and it will kind of fall its way down, kind of like a Plinko machine, all the way down into the right bucket that has the right color for it. And you're done. You've classified, you've sorted basically what that data point is now using a decision tree. Visualizing that, that's what that looks like on the graph. So each one of these lines represents a boundary. So instead of like kind of the diagonal lines that you get from just a regression, each one of these is a boundary aligned with some number. So this one is a boundary, a vertical boundary aligned with one of these parameters on the horizontal axis. These horizontal lines are boundaries associated with a line on the vertical axis. Now again, they're not really x's and y's per se. You can think of them as x's and y's on a grid, but they're really just two features. Remember, two features. x1 and x2, usually more to differentiate. Because one is not necessarily dependent on the other. We care about the class, the color of the dots, not the x or the y values. We use both of those to separate it into x and y. Okay, so to wrap up then, there's a lot more to supervised learning, and as you get more and more data, it becomes difficult to maintain those labels, those colors, those outputs. And then we can turn towards unsupervised learning where we can pull a human out because humans are a little bit expensive sometimes when working with data. And that's all part of the grand world of machine learning. But given our time, I want to wrap up with something more relevant, or what the current state of the art is per se, which is deep learning. Deep learning. All right, so neural networks. You've probably heard of a neural network before. A neural network is a biology-inspired, though not biology-representative, model that's implemented in a computer or a numerical sense that can help make decisions for us. It comes from neurons. Now, here's our simple image of a neuron. A neuron effectively takes information in, does something to it, and then passes it on to the next set of neurons. So that's just one. So that means if we have multiple neurons, information comes in on one, gets passed down to another after a little bit of transformation. That's it. That's all it is. A couple of small individual units that take an input and an output, and then when you combine them together, you form a network of inputs and outputs. Now, turning this biology-inspired approach into a more abstracted one for our numerical purposes, we can replace these with some dots, some circles, and these circles represent then the transformations that we're going to. Now, this is a very simple neural network per se. These dots on the left, we're going to call these the inputs. That's where our inputs go, our data effectively. And then whatever's on the other side is our output. Okay? So now let's use this to solve our classification problem again. Here's our classification we started with, 2 dots, red and blue. Okay, but now we're going to try to represent it with these dots. Well, one of these dots is an input, right? So the inputs that we have are a number on this horizontal axis and a number on the vertical axis. So we'll call them x and y for easy sake. So we'll put our x and our y as our inputs. Our output is the color, the class of each of those dots, so that's what we'll put over there. Now I need to turn this little abstraction into a way to take an input, that's an x or a y, and translate it to an output, a red or a blue. Which one is it going to be? How am I going to combine it? Well, I could just put the x's and the y's in there directly, and that'll do well enough for 2 data points, but it gets a little bit fuzzy, right? So let's add a little bit of extra information in here. I'm going to add a weight, essentially how important the x is. I'm going to say the a value weights more for the x, and then the b value weights more for the y. So the more important one of those 2 inputs is, you put a higher number in either A or B, and then that becomes a more important input for helping to determine what the output is. Okay? Easy enough. Well, does anyone know where we're going with this? Yep?
Do that with a bunch of extra layers to get more and more knowledge.
Okay, even before the layers. How do I combine these? There we're going. We are going there next, yes. How do you combine these? We just add them together in an easy enough way. And if you do, what does it become? Just a line again. Just the same as a straight line. A simple, very simple neural network is effectively the same as a linear regression. In fact, one layer of these, you could have multiple x's and y's, x1, x2, x3, all the way to xn, right? Much like our linear regression. You could do that, and it would come out to a similar equation. It's effectively a linear regression, ignoring a couple pieces like an activation function. We'll talk about that in a second. But this equation down here is not quite the same. There's something missing, right? What's missing in my neural network? The c, right. So if we're going to complete this out so that it's equivalent, now I know the linear regression works, so if I want to equate that, I need to add the c term in there. The c is also an input, but it doesn't necessarily have its own weight or its own input value. It's just one by itself, right? There isn't an input times something. It's just c, and this is called the bias term in the machine learning. Now, pretty much all neural network layers will have a bias term as well as any other inputs and weights associated with it. Okay, now, this is great. This works. Neural network. What happens when we get nonlinear again? Can this equation or this simple neural network, as I've drawn it, separate a nonlinear data set like the curved ones that we just saw before? Well, it can't, right? We set out that the linear version, linear regression can't. We had to get nonlinear with that. Same thing here. If this is all stuck in the linear realm, it can't separate nonlinearly separable data. Now, there are ways around that. The 2 main ones are to use an activation function. So that says that at the end of this equation right here, I'm then going to take the output. Instead of then comparing it to a number, I'm going to pass it through something called an activation function, which is another mathematical function that takes whatever the computed sum is, the sum of the linear regression, and then modifies it by some other function. Common ones are called a ReLU, rectified linear unit, stepwise function, tanh, hyperbolic tangent function, sigmoid. There are some others as well, but these are certainly the most popular ones. All of these are nonlinear functions. Nonlinear functions. And so that adds an element of nonlinearity to it and allows your neural network to get a little bit more curved around the data, however it likes. The second piece is with those hidden layers that were mentioned there. The hidden layers means that instead of just one neural network or one input and output, let's just take the output and make that the input to another set of outputs. So we have input, then another layer of these nodes where things get multiplied together with the weights, then summed, and then passed to an activation function. And then that becomes the input to another layer that gets summed with weights and then passed to an activation function. That's what's called a hidden layer if it's between the input and output. However many layers there are between the input layer and the output layer are hidden. The more of those we have, the so-called deeper our network gets, right? From beginning over here all the way to end, it gets deeper. You can have however many you like. The deeper you get, we arrive at what's called deep learning. So whenever you hear someone refer to deep learning, it means working with neural networks with a lot of hidden layers. That's all it means. Okay, so to wrap things up then, coming back to ChatGPT. Now this is not the current model, it's from a few years ago, but the GPT-3 model, which is the first one that OpenAI made public after training, had 96 of these layers, where each layer is comprised of a whole neural network. 96 layers, 175 billion weights. So the A's and the B's, or the W0, W1, W2, etc. 175 billion of them. This right here is effectively the entire model that allows to answer your question about whether or not the sun is going to rise tomorrow. Each one of these little blocks, okay, there's a pair of blocks. This is what this model looks like, the GPT-3 model looks like. Compares of little pairs of blocks. Each one of those pairs of blocks looks like this. One of those pairs is called the attention block, or attention layer, and the other one is a multi-layer perceptron. Perceptron is the original name for the simple neural network, or the simple neuron, back when it was developed in the 50s. Okay? That was what they called it, perceptron. A multi-layer perceptron just means you have multiple layers of it, like we just talked about. Okay, so inside each of those layers, they look like this. This multi-layer perceptron, similar to what we just saw. Right? We've got a whole bunch of inputs. It passes through a hidden layer, and then has an output that then gets passed on to the next whole block. Now, in between these multi-layer perceptrons is this other block called an attention layer, and this is what allowed these neural networks to be particularly effective nowadays. Now, the attention layer still is a neural network. It still has inputs, a hidden layer, and outputs, except now the only difference is that the hidden layer is informed by other parts of the model. So rather than training up these weights through some algorithm, some optimization algorithm, now these weights get chosen based upon the performance of other layers. The idea with attention is to bring more focus to more important combinations of words, for language models at least, and then less value to less important combinations of words, and that's what informs that. But all of those combinations of those pairs, 96 of them add up to the GPT-3 model. GPT-4, or 3.5 and then 4, and a lot of the other ones out there, your Google's Gemini model, the open source models out there, Mistrals, Olamas, etc., Meta's models, they all look something like this, with some combination. They have some different tweaks in them, a couple of different layers interspersed, but invariably they all have at least some iteration of these two types. And slap on the switch, and in 10 seconds time, your homework comes out quick and clean as can be. And here it is, 9 plus 4. The answer is 3. 3? Well, I guess that's not as perfect as I thought it could be. That's what I have for you today. Thank you.